Cool. All right. So hi, everyone. My name is Preston Engstrom. I'm a data engineer at RBC. I almost said Scotiabank because I used to work there. I graduated from computer science at Brock University about 3 years ago, and I've been working in industry ever since, mostly in data science, data engineering roles. So we're just presenting this paper about large-scale parallel collaborative filtering for the Netflix Prize. It's an older paper from 2008, and I'd just like to thank Serena and Omar for being really great and helping me get this together on such short notice. So thank you very much, guys. I appreciate it. So just a little bit of a coverage of how we're going to format the presentation. We're going to start with just a bit of historical background. I don't know if everybody here is familiar with the Netflix Prize, but it's worth exploring the context of the prize and the data set that they use. Then we'll go a bit into how the problem of alternating least squares for collaborative filtering is formulated. Then we'll talk about some of the results and move into the discussion. So the Netflix Prize, it's quite an interesting little piece of internet history. I always joke about it as it's the cheapest R&D team any organization has invested in, because for $1 million, they basically turn the entire internet into data scientists trying to figure out how to make them be the best of the best. So the way the prize was formatted is in 2006, they released this data set of 100 million ratings. So those were user, item, the date that they made the rating, and the score of the rating. Those ratings were distributed over time, starting from 1995 to 2006. And using that time scale is how they split between their training set and test set. And the training set is split between a train set and a validation set, which for the purposes of consistency, we're going to call the probe data set, but it's just a validation data set. And I'd just like to take a moment to look at what the winners' scores were. I should mention that the goal of the prize was to beat Netflix's current best algorithm in terms of root mean squared error by 10%. And I'd just like to point out that there are two people who got the exact same score. So one team missed a $1 million cash prize by 20 minutes in their submission time. That was the tiebreaker. So spare a thought for those guys. So a lot of people sound like they have backgrounds in recommender systems, and as such, we'll just quickly cover collaborative filtering for anybody who's not familiar. So basically, the idea is you have a population of users who have interacted with items in some way. Maybe they've said they like or dislike it. Maybe they've rated it on an explicit scale, like 1 to 5 or 1 to 10. Or maybe you are building some implicit feedback from their interactions and kind of trying to gauge how they like a product. That's out of scope for this talk. We're only dealing with the explicit case, but it's something to think about. The idea with collaborative filtering is you look at the history of what a group of users liked or disliked, and users who liked or disliked similar things can be used to tell you what other people will like, even if they haven't interacted with it at all yet. This is kind of contrasted with a technique called content filtering, which is more of looking at the attributes of users and the attributes of items to see how we can kind of cluster them together to make recommendations. So this is the fun part, going over a bit of the notation that if anybody has any questions or wants clarifications, please, when we're looking at some of the formulas, don't be afraid to say, hey, what does that mean? So we have n sub u, the number of users, n sub m, the number of items, in this case, movies or shows on Netflix. R, which is our users by items recommendation or ratings matrix or interaction matrix. Rij is the element of user I at item j in the interaction matrix. So if it's populated, that means they've rated the movie or the show, and if it's not, they've had no interaction. Then we have capital I sub I, which is the set of movies that user I has interacted with. We have nu sub I, which is the cardinality of I sub I, the number of movies they've interacted with. And the same thing for items. So I sub j is the number of ratings that are for item j, and the cardinality is n sub j. So how do we think about this problem? So we're given a set of users and items, and we want to estimate what a user would rate an item that they have had no interaction with. So as we said, we have the user ID, the item ID, and what rating they gave it. So a really common approach is a low-rank approximation, low-rank matrix approximation algorithm. The idea being you have this massive matrix. It could be millions of users by millions of items. And we want to be able to very quickly break that down and understand how to make predictions. So we take that matrix and split it into two smaller matrices. We'll call them U and M for users and movies. So each row or each column, depending on how you format your U and M, are basically a dense latent representation of a user or an item. And the inner product, or the dot product of those two vectors, are going to give you the prediction for the rating. So just a little graphic to kind of make that a bit more clear. So U is basically a matrix of vectors in space of the real numbers, where for each row, in this case, each row represents a user. And for the movies, each column represents a movie. Given that the Netflix prize is over 48,000 users and 48,000 movies and I think quite a few 100,000 users, that's a lot of parameters to learn because each index of those kind of dense matrices are a parameter. So we have to consider how we're going to approach that problem. So the way that this approach kind of looks at it is we want to look at reducing some score, some error function for all of the ratings that we know. In this case, they use mean squared error. Mean squared error. So basically, the difference between our known rating R for our known data and the inner product of our U and M matrices, our U and M vectors squared gives us our loss. So over the entire set of ratings, that's just the sum of all of that empirical loss divided by the number of ratings. And so we want to minimize the error of a given U and M over the entire matrix. But because we're fitting so many parameters and we have a relatively small number of ratings for each movie and each user, because it's impossible for somebody to rate a large proportion of any given item base or any item to be rated by like all of the users. It's very unlikely. We want to introduce a regularization term because there's going to be a lot of bias based on the viewing habits of people. So we'll get more into a bit of that later, and this is just the regularization term. So it's a Chikhanov regularization, which is really common for least squared problems. So a really common method that people talk about when they think about matrix factorization in a lot of contexts is singular value decomposition. And one of the first things I thought in this paper was when they start talking about it, well, why didn't they just use SVD? And the difference between the approach we're going to talk about in SVD is that SVD looks at the norm, the Frobenius norm of the entire matrix. So it looks at every index ij for all ij, regardless of if there's been an interaction. And because we've already talked about how it's impossible for a matrix to be mostly populated in these kind of contexts, you're going to get really kind of weird answers. It's going to be really difficult to find a good U and M. So rather than looking at the entire matrix, we're going to try a different approach. So alternating least squares works in a really similar way, the exact same format of our matrices. But we start by initializing them, using one to update the other, fixing the newly updated matrix, and using that updated matrix to update the other, and alternate back and forth. So we're looking to solve a linear least squares problem for the given ratings, using a given matrix, and using the result to update the other matrix.
I didn't quite get the difference. I got the difference, but is the motivation that SVD would be computationally too expensive?
It would just fail to find. So if you're trying to learn all of these parameters over every element of your interaction matrix, there's going to be a lot of noise for every unknown rating. So you're basically going to just take forever, several more iterations. Yeah, computational time, and there's a lot of people have tried it, and there are extensions to SVD that make it work quite well, but that's outside of the context that these people had writing this paper.
So
that
you're saying
clarifies.
That there is both computational expense, but also a chance that it might not even converge to a solution?
And the authors also mention that it's standard SVD that you can't apply directly because that would require them filling in those missing values with 0. So that's assuming that the person didn't rate the movie, assuming they didn't like it, but that would enter some noise into the system.
Cool. So this is just a little breakdown of the algorithm. So we start by initializing our movie matrix M, which is an NF by NU matrix. And NF is just the number of free parameters we have for each user or item. So you can think of each user as a NF length vector. So we assign just random small values to this entire matrix. And one of the things that the authors did is for each movie, they assigned the first element of that vector to be the average of all ratings for that movie. We can talk a little bit more about that in a moment. Then we fix M and solve U by minimizing our objective function using just a linear least squares. And then we use that newly updated U matrix, fix it, and solve M using the same method. And we just repeat this until some stopping criterion is reached, whether that's the number of iterations or some minimum increase or improvement in the loss function. In this case, they just set it to 0.0001. And that's not on the training data, but on the validation data, the probe data set. So every iteration, they're calculating their total difference in mean error for the probe data set. Get a little bit more into their loss function. So it's, again, just root mean squared error, but they have this regularization function here, which again is Chikhanov regularization, which I'm never going to be able to say properly. But the idea of that kind of regularization is,
in the last slide you said that you assign it, like you initiated with the average value of a movie that the users have given. So consider you have a movie no one has given a rating to. So you initialize it to 0 or you just leave it null?
That's a good question. And one thing that the Netflix prize dataset did was they made sure that every movie included had been rated exactly once. So once you get into a situation like that, we call it the cold start problem, right? You have a new user introduced, you know nothing about them, how do you recommend? And that's a challenging problem, but this doesn't deal with that case.
No, it's not about the new user, about a new movie that has no rating. Like that's not been rated by anyone, so you just remove it from your dataset?
Yeah, it wasn't included in their dataset at all. But it still is the same idea, right? You have no information, so you can't really make a recommendation.
So, sorry, you said each movie is rated exactly once? Or
At least once.
Okay, got it.
So where were we? We were at the regularization term, that's right. So the idea behind Chikhanov regularization is you have some value that you're going to multiply a identity matrix by and use that in combination with the norm of whatever vector you're using. In our case, it's the dense representation of the user or the item vector. And what that's going to do is it's going to penalize elements with high error. So in this case, they selected 2 counts, which are basically the number of users that had rated a movie for this value here, and the number of movies a user had rated. The idea being that if something had a really high error and a user had rated a lot of movies, or a movie had been rated a lot of times, they would want to try and scale that back because of some bias that might be introduced. And they do mention that they tried several other schemes, and this is the one that worked the best for them. So I don't know if anybody here is super familiar with linear least squares like in the guts. I think most of us should be, but this is just showing how they take their loss function and derive basically their formula for a solution. So the idea is, given a linear least squares type problem, what we want to do is we want to set the derivative to 0 and then use the resulting equation to solve our least squares problem. So we can see they just set the derivative of the loss function to 0. And from there, it's just algebra to get to the point where we're solving for an individual user vector. If anybody has any questions about going into this, let me know. Shoot.
I think in practice, generally, it's not a good idea to find the inverse of matrices. I'm not sure about this paper, but probably iterative method to get to the minimum usually is used. Because if the condition number of that matrix is bad, it's very large, then the inverse is going to be computationally so unstable that you won't be able to find a good inverse. When you're thinking about large matrices, it perhaps that could have very large condition numbers. Now I'm wondering if they actually took the inverse of A in the paper.
No, I don't think so. Do you?
No.
Can you speak to that? No, I don't think that's them finding the inverse of the matrix. I think that's
Generally not a good idea.
yeah. Okay. I think can you speak to that? Because I'm not super familiar with the inverse of matrices, but I know that's not what they're doing because, like, they don't encounter issues of computational complexity in this, so.
Yeah, they don't make any mention in the paper about computational complexity except for the parallelization part.
And this is also just the standard form for a regularized linear least squares problem, right? So I think that's not the inverse, but 1 divided by the matrix. I think that's just
I think that's the key.
clever
The
notation.
A here is actually a submatrix. It's not the full 18 matrix. It's a submatrix with much smaller size. So even getting the inverse of it is possible at that point.
Oh, you know what? That is a good point that I'm sorry I glossed over. So what we're doing here is this is the formula basically to update for a given user. So at this point, we're solving for all I over all k. And that means, so given a user's kind of dense representation, we're updating each individual index of that vector. What they've done here is they've just kind of condensed that notation to treat them as matrices. But what I sub I is it's the submatrix of all the movies that user I has rated, which, as Omar said, is generally going to be quite small. Thank you, that was a good question. So this is just a little toy implementation of the algorithm that I wrote up in Python just to kind of get my head around it and understand how it worked in practice. And interestingly, on a slightly smaller but similar data set, the movie lens 100K, this runs pretty fast, like just a few seconds per iteration, so it does quite a good job. But so you can see, so for that same update U procedure that we were just looking at the formula for, we take our lambda value, so our regularization parameter, multiply it by an identity matrix. We set up our new version of U that's going to become our updated matrix and just initialize it all to 0. And then for every user, because I have my interactions matrix in a way that's every column is a user, so index the first axis is going to be the number of users. We get the submatrix of the movies that the user rated. We get the movies user rated. Oh God, what am I doing there? I'm sorry, I'm having a brain fart here. MU. Oh, that's right. So this is an index. So we're using those index to select those relevant movies from the dense movie representation matrix, and getting our one term for our least squares problem by multiplying that matrix by the ratings that a user has given. And then the second part is just getting the multiplication of that movie submatrix by itself, and then adding the regularization term. Is that clear? Everyone's okay with that? So the other kind of thing that the paper points out is that this kind of least squares problem is really easy to parallelize. So for every alternating update, you can update portions of U or M completely independently of one another. And the way you do that is you partition whatever matrix you're updating across multiple nodes, multiple computers. But what you need to do is for every node, you need to have the fixed matrix in its complete form, because you can't split it up, because you're going to have to go to other machines to look up movies that have been rated by a user, or vice versa. So you broadcast out a copy of the fixed matrix and use it to update the partitions of the matrix and alternate that back and forth, which greatly speeds up running time. I believe they said for one iteration in a single machine, it took them 3 hours on the Netflix Prize dataset in 2008. And parallelizing over 30 machines using Matlab, I think they did it in about 20 minutes for each iteration. So that's a really significant speed up. They also discuss a few post-processing techniques that they use to improve the score of their algorithm. One of them was just a global mean shift. So given a predictor P, if the mean of that predictor for a given set of data is not equal to the mean of those ratings on the data set, they just shift all their predictions by the difference. And that's used in a lot of contexts, and it's been shown to strictly reduce RMSE. And the other one is linear combinations of predictors. So basically, given a set of different predictors, you can use a linear regression basically to find a parameter x that lets you combine their predictions and also not strictly improve RMSE, but basically make it perform at least as good as the best predictor among them if it doesn't improve them.
What is the justification of the global mean shift?
So in this case, that if you know, I'll take it.
Please.
So when you're predicting something, you eventually want the root mean squared error to be almost 0, right? And for that to happen, if the mean of the prediction, after prediction of the matrix you actually predicted has a totally different mean than the actual or the original matrix, this is going to give kind of a bias. And the best way to reduce that root mean squared error is to remove like the average between these two matrices. And it, yeah, as he said, it actually reduces the RMSE by a lot.
I understand that. What I don't understand is, like, how did they know that the error introduced is a bias rather than some sort of variance?
So usually, the one thing about a recommender system is if users, like let's say we have 3 different users, the 3 different users are going to have totally different tastes and totally different ways of ratings as well. And this is one of the ways to normalize kind of the whole, for the 3 users are going to almost have the same rating, is by combining them and finding the average and taking it away from the predicted one. Because for example, if Preston and I watch the same movie, and usually Preston is a very nice person, is going to give it a 5, even if, and while me, even if I like the movie, I'm going to give it a 4, that's kind of unfair decision or bias, right? So what, at that time, 2007, that's what they did. They took the average of the whole matrix, while right now, actually what they do is they take the average rating of each user and they remove it from, they normalize it from the user base instead of the whole matrix. But that was 2007, so yeah.
Cool. All right, so I guess we'll move into the 2-minute break with that. If anybody has any questions before we do that, it would be a good time.
I have a question. If you go very at the beginning of the slides, there was the matrix factorization visualization of U and V, U and M. Yeah. Did they mention what is the dimensional? What is the reason behind choosing 3 for the?
That was just a demonstration for this visualization.
What was the actual latent dimension?
They when we get to the results, they do experiments with multiple.
Okay.
Okay. So we'll jump into the 2-minute break.
I have a question.
Go.
So take up to the optimization part.
This one?
Even before that. Yeah, for this one, right? Yeah. So you update and fix you,
Correct.
and you update it and so I could be really wrong here, but that takes you to like the optimal solution. The problem is convex, right?
Yep.
Is this convex optimization problem?
Trying to update them both is a non-convex optimization problem. That's why we fix one and update the other using linear least squares. They mentioned in the paper that previously people have tried to update them using stochastic gradient descent, and it takes a very long time. People have had success with that in the future. We can talk about that after, but at this time it wasn't really a tractable approach.
But it doesn't take you to global optimum, right?
I'm not
Does it
certain.
depend on the
Not necessarily. That's true. Doesn't necessarily.
Yeah.
like you don't, like maybe they thought about like
If you have an ill,
different starting point and different solution.
yeah.
So yeah, it doesn't guarantee like optimum solution, but the way they had it is the stop criterion was 0.0001 as the root mean squared error, right? So
That's the effective of a minimum, right?
yeah, so again, it doesn't guarantee.
But that doesn't mean
Yeah, like
maybe starting with different starting point. It takes you to different solutions, right?
Yeah, absolutely, but that's also why they introduce a regularization term and test it out. But They've had good success with it, but it can get stuck in local minima, of course.
Hi everybody, welcome to TDLS. I'm Lindsay, I'm one of the members of the steering committee. If you liked the video you just saw, subscribe to our YouTube channel and you'll be the first to find out about every video we put out.